The sheets that you have today deal with a topic that is going to pull what we've learned in the last maybe 4 or 5 sessions together into one. But we'll start the topic slow, and we'll go through an individual formula first, and then we'll see how things tie together. First of all, please watch the introductory video on YouTube that I linked to. It gave a couple of good examples of what friction is, and just reminded you maybe some of the general terminology regarding friction before we get into the specifics on these pages. So I'm going to go through this slow. This video should take between 20 and 30 minutes. Let's start off with some preliminary notes in the beginning. So what I have here is I just put a diagram here of a 50 kilogram mass that's sitting on a flat surface, and I want to put a diagram here that you can just leave in your notes and refer back to as sort of a study key. So there's not going to be any formula here. Let's just look at a general situation. So you have a 50 kilogram mass, and let's say you're forcing it forward, and I'll just make forward to the right. So I'm just going to draw a force. Now, as you know from some of the previous work that we've done, just because you're pushing forward with a force doesn't mean that that's going to be the overall force that is present in the question. So what we're going to do is we're going to start labeling forces with some really specific words in the lower right hand corner. And you've already done this. You've already been labeling net forces with a more specific word in the bottom right hand corner. Now you're going to see a couple of others being thrown at you here. So this force is called the applied force. And what applied means is kind of just how it sounds. This is a force where you're actually applying the force with some external means. It could be muscle power, it could be an engine, but this is a force where you're actually pushing the object. Now with today's topic, force of friction, opposing that force in an equal and opposite direction that opposes motion is going to be a force of friction because of the contact between the two surfaces. So remember, whenever you have contact between two surfaces, you have to have friction. So there's a force in the opposite direction, and like I said, I want to label every force now. So in the lower right hand corner, I'm going to put a little F. Friction. So here's our general situation. You're pushing forward with some kind of an applied force. There's contact between the mass and the surface, so there's going to be a force of friction, and that's going to be in an opposite direction. And when you consider those two forces, what you push with and how much you have to take off because of friction, that will give you your overall net force. And I'm going to draw that off the diagram kind of on its own, and I'll even make it a slightly thicker arrow just to stress that this is kind of the overall situation now. And then in the end you have your net force. So there's the general situation. And if you can think about this, this is what we're going to be doing. We're going to be taking applied forces forward, in most cases, subtracting off friction, getting an overall net force in the end, and then when you get the overall net force in the end, that's where you can start calculating from that acceleration, where acceleration is net force divided by mass. So it's not until you have that overall net force that you can calculate the acceleration, and then continue on in the question if it asks you things after that. So this would be the normal situation. That would be really all that's in the diagram. But as you're going to find out very shortly, the formula for force of friction is going to involve some other things. So there's 2 other forces I want to label on this diagram to kind of make it your study key. There's always a downward force. That can't be avoided because we're on a planet that has gravity. So there's always a force of gravity in the downward direction. And remember, objects will accelerate in the direction of an unbalanced force. So if there's a force of gravity down, there would be acceleration in the direction of that force because there's nothing else to cancel out that force. Well, that doesn't actually happen. you're sitting on something right now, or whether you're laying on your bed, or whether you're sitting in a chair, or whether you're in a classroom sitting at a desk, there's a force of gravity on your body right now, but you're not accelerating in the direction of that force, which means there has to be an equal and opposite force in the upward direction that cancels those two forces out. And there is. There's one more force. Whenever you have an object in contact with a surface and being forced into the surface, in this case with gravity, there's always a reaction force where the surface itself pushes back. And we call that force the normal force. Now be very careful, because normal starts with an N, and so does net. That starts with an N as well. So I've noticed students in the past in grade 11 will often get things confused in questions because they will confuse the net force and the normal force simply because most students only use one letter in the lower right hand corner. So my suggestion to you, my recommendation is either write these words out, or if you're going to write just a little letter in the lower right hand corner, maybe always write out F net as a word. And you can make these other ones just a single letter in the lower right hand corner. But you will eventually confuse normal force and net force. You won't confuse them in concept because they're clearly two different forces, but you may consider them when you get into formula calculations. Okay, this diagram doesn't have to make sense yet, but it will. It will as we go through the work. Just keep those four forces in mind. Those are the four forces that you will find in virtually every question, and a fifth force if you think about it, because gravity and normal cancel out, and then applied force and friction, you work those two out and get your net force in the end. So why even bother having these two forces here? Why even bother having normal force and gravity if they end up canceling each other out? Well, that's going to become obvious in a few minutes when we get to the formula. So first off, when does one encounter a force of friction? Well, you can write down in this blank, and by the time I write it down, you could have had it written down twice. So when does one encounter a force of friction? Whenever two surfaces are in contact. We don't have frictionless situations. Even if you get into the most smoothest, slipperiest surface of ice, there's no such thing as a frictionless surface. So I'm just going to quickly write down whenever two surfaces are in contact. And you can continue this and say there's no such thing as a frictionless surface. Space, outer space, if you're moving through space, it's generally considered frictionless, but there's no surface. If you were in contact with any surface, there would be friction. In what direction does force of friction always face? Friction's one of the rare cases where you can always state what the force of, or sorry, what the direction on it is going to be. It always opposes motion. That's not true for every force, that you can always state the direction that it's going to be in. But friction, the only way that you can have friction is in the opposite direction of motion. What is the force of friction formula? Okay, well this is one of the reasons why I wanted to draw that diagram up at the top of your page. Now if you did the pre-lesson readings for this, you've already experienced what the force of friction formula is, but that's okay. I'm going to write it down right here. So force of friction, so I'm going to write a capital F with a lower f in the right hand corner. Force of friction, there's only two variables in this formula. It's a really easy formula when you actually pick up a calculator and you need to calculate. However, the first variable in this formula, it's perhaps the first time that you've seen this or tried to write it, it's a Greek Latin symbol. It looks like a capital U, but there's a little bit of a sort of a squiggly little tail there on the front of it. So write that down, and we're going to multiply that by another force, Fn. So there's your formula for force of friction. There's only two things in it. Force of friction equals coefficient multiplied by the normal force. And maybe since this is the very first time I've written it down, I'm going to complete this and write the word normal in there. Although you probably won't want to do that every time. But there's That's why, if you look back at this diagram, that's why I put these two forces on here and canceled them out. They do cancel each other out, but the thing is, to calculate force of friction, you actually need to know what the value of the normal force is. Because whatever the normal force is in a situation goes right into the friction formula. So we need to calculate normal forces in order to do these questions. Let's take a quick look here in the very last spaces here. What are some more details that you need to know about that weird symbol that I just wrote down? Well, number one, it's called the coefficient of friction. Coefficient of friction. So this is a value that describes the, I want to say friction, but I can't use that word in the definition here. It's a value that describes the stickiness, let's say, between any two surfaces that are in contact, any two materials. Coefficient of friction. It describes the stickiness. I'm making up my own words now. Would I put an I or a Y? I don't know, I'll check that out later. It describes the stickiness between any two surfaces. But it changes. It's a different number for every combination of surfaces that you can possibly imagine. Well, just think, there's millions of different types of surfaces. And there's millions of other surfaces that could be in contact with that surface. So the combinations of surface and surface contact that you can have is so vast that there's reference books and reference books and reference books that do nothing but list coefficients of friction. As a little hint here before we write any further, that's what the next page is. I just took a small snapshot of one page of a chart that lists the coefficients of friction for some really common materials that you find in this class quite often, like rubber on concrete, because we do so many questions with roads and cars on roads. Steel, ice, wood, very common objects. But you see every single one of these is a combination of two materials, leather on oak, rubber on ice. When you look up these things in reference charts, you get the coefficient of friction. And there's two different columns, but we'll get to that in a minute as well, why there are two columns. Let's go back to the first page. So, at the bottom here, what are more details I should know about coefficient? It's the coefficient of friction. It describes the stickiness between any two surfaces. It is it's just a value between 0 and 1. Some decimal somewhere between 0 and 1 in 99% of the cases. It's a value between 0 and 1. It's actually a ratio. And we'll get into how you experimentally determine coefficients of friction maybe at another time. But it's a ratio, which means because it's a ratio, it's unitless. So it's not in meters, it's not in meters per second. Here, maybe I'll change that to a therefore. It's a ratio, therefore it's unitless. Yeah, not meters per second squared. It's not in kilograms. This is just a value that is just a value. Value between 0 and 1. And as you get down to 0, this would be more slippery, if you want to consider that a term. And as you get up to 1, that's where you get a lot more sticky. So somewhere in between is a value that is going to describe the situation of materials that you have in contact. And there's one more thing I need to add, and I kind of filled in too much space here with that, so now I'll put it over here at the side. There are two types of coefficients. There is static and kinetic. And that's why on the chart that follows on the next page, there are 2 columns. How can I describe this? I'm sitting at a desk here in a room at St. Michael. I'll just put my calculator here on the desk. When you have an object that is stationary and it hasn't moved yet, I'm sure you've noticed this before, it's a little tiny bit harder to push it and get it into motion than when it finally does get into motion. When something's in motion, it's very easy to keep it going. Think of a very heavy table, or let's say a fridge. You're helping somebody move. That stationary object tends to compress into the surface underneath it a little bit more than when it's actually in motion. And that's why there's 2 types of coefficients of friction, static and kinetic. Static means stationary. That's an easy thing to remember because it starts with the same letters. Static is stationary, kinetic is moving. So when you look up coefficients of friction, there's slightly different values depending on whether the object that is being moved is at a standstill in the beginning or whether it's actually moving already. So when you look on this chart, let's just take for example wood on